Hello everyone, so today we are going to be talking about prime numbers, starting with problem 1. Find the prime factorization of 97. So when we're checking for prime factorization, we check for primes that are under the square root of that number. So if we have a number like 97, we have to check for all primes under square root of 97. And the square root of 97 is less than 10. Less than 10. And I know it's less than 10 because the square root of 100 is 10. And alright, so we're going to check for all square roots less than 10. Well, we know the divisibility rules that we learned from before. So we need to check for divisibility from 2, 3, 5, 7, and that's about it, yeah. Oh, but we don't have a divisibility rule for 7. So we know that 9 is not divisible by 2, last digit isn't even. It's not divisible by 3 either, because 9 plus 7 is 16, and 16 isn't divisible by 3. Not divisible by 5, because the last digit isn't 0 or 5. So we just need to see if it's divisible by 7. And, well, actually, if you just recall, 97, 7, 1, 7, 27, and it is not divisible. So we can safely say that 97 is a prime number. And back to the rule that I said before, why do we need to check for all primes less than the square root of n? Well, if you look at a regular number, for example, a non-prime number, so a composite number, if you look at a number like 20, let's list out all of its primes. Let's list out all of its factors. So one factor is 1, 2, and here we have 20 and 10. Not 3, but 4 and 5. And if you look at the square root of 20, the square root of 20 is 2 square root of 5. So 2 times the square root of 5. Square root of 5 is greater than 2, but only by a little bit. So we're going to say around 4-ish. Around 4 to 5, well, I suppose. So if you have the square root of 20, then square root of 20 times 20 would equal, square root of 20 times square root of 20 would equal 20. So it's right in the middle of all of the factors. And then 4 times 5 is equal to 20. And then 2 times 10 is equal to 20. 1 times 20 is equal to 20. But the important thing to note is that if there is a factor less than the square root of 20, there is also a factor greater than the square root of 20, and vice versa. So for every factor less than the square root of 20, there's a factor greater than the square root of 20. So we only need to check if there are factors here, and we don't need to check more than that. We don't have to check up to 20, because we can just divide the number of factors in half like this. So we only need to check for 1, 2, and 4 in this scenario. And so the same rule applies to 97, right? So 97's factors look something like this. We have 1 and we have 97. And then somewhere in between we have the square root of 97, which we said was less than 10. So we only need to check up to 10 in order to figure out if 97 is prime or not. Because, okay, I think I've explained that enough. I do have a tendency to over-explain, I guess. Alright, problem 3. Find the greatest common factor of 100 and 1000. Alright, well, greatest common factor of 100 and 1000 must be 100, right? So I'm going to draw a Venn diagram of all the factors here. So one of the factors it shares is 100 and then 10. So this is the box for 1000. This is the box for 100. And so 100 is in the 100 box, and then 1000 has 100 times 10. And that's how I'm going to explain my Venn diagrams from now on. These are all the factors though. So I suppose it would make more sense for me, instead of having 100, I would have 2 times 2 times 5 times, 2 squared and times 5 squared. And for here, I'll rather have 2 times 5. And we multiply all this in order to get 1,000 here and 100 on this side. So the greatest common factor would be these numbers right here. And that would be 4 times 25, which is equal to 100. Greatest common factor is 100. So the least common multiple of 100 and 1,000, well, the least common multiple would be taking this right here multiplied by this right here. So 2 to the third times 5 to the third, which is equal to 8 times 125, which is equal to, yeah, 1,000. So we just solved both of our questions, 3 and 4. The greatest common factor is this right here. So all the factors that are shared between 100 and 1,000. The least common multiple is, well, we want to minimize it, right? So we have the number of shared factors already, and then we multiplied by 2 and 5 in order to ensure that it's also a multiple of 1,000. So we get 1,000 is the least common multiple. And problem 5 is show that the product of the least common multiple and the greatest common factor of two integers is equal to the product of these two integers. So if you look at our Venn diagram here, and this is just an example, it's not a formal proof, but if you look at our Venn diagram here, you'll see that if we multiply this bit right here, so I'll say right here, so 2 squared times 5 squared, and we multiply this, so this is the least common multiple, right? Greatest common factor. This is the greatest common factor, right? We take this, I'll say greatest common factor is equal to this, and we take the least common multiple, which is equal to 2 squared times 5 squared times 2 times 5. If you multiply these two together, you'll see that it's equal to 100 times 1,000. Because you're taking this part, well, 1,000 is equal to this part, all of this whole thing right here, right? So 1,000 is equal to 2 squared times 5 squared times 2 times 5. And 1,000 is equal to this part, or 2 squared times 5 squared. So if we say 1,000 is equal to this, and 100 is equal to this, and we multiply this and this together, then you'll ultimately reach the conclusion that by multiplying the greatest common factor, or this number, by least common multiple, or this number, you'll get the square of the product of these two numbers. Or sorry, the product of these two numbers, not the square. Okay, that's a little bit too much. But yeah, the product of these two numbers. And you'll see that I think this is 100 and 1,000 might not be the best example for this problem, because 100 doesn't have any unique factors in this space right here. So I'll do an example with another set of numbers in order to make sure you guys understand that when you multiply the greatest common factor and the least common multiple, you get the product of the two numbers that you're taking the greatest common factor and least common multiple of. So let's say you have a number like 12 and 12 and 36. Or maybe that would be too much weight. You have to have some. So I'll have 2 times 2 times 3. So it's 2 times 3 times. Okay, that should be you have two numbers, 12 and 30. And I'm going to draw the same diagram that I had before. This is for 12, this is for 30. We're going to put in their factors in this box. So two factors that they share is the 2 and the 3. 2 and the 3. So 2 times 3. And the factors that they don't share is this extra 2 right here, this 5 right here. So if you look at this, greatest common factor is equal to the greatest amount of factors that they share together, which is 2 times 3 is equal to 6. Least common, I'll just leave it as 2 times 3. Least common multiple, well, we already counted 2 and 3 once, and even though they share it, because they share these two, right? But we also have to multiply an additional 2 and multiply an additional 5 to make sure that the number is divisible by both 12 and 30. So we have 2 times 2, which is 4, times 5, 20, times 3, 60. So we have 2 squared times 3 times 5, which equals 6, which is equal to 60. Yeah. I'll make sure that this looks more like a square. Alright, and we're saying with our Venn diagram that 12 is equal to 2 squared times 3, and 30 is equal to 2 times 3 times 5. So when you multiply the greatest common factor and least common multiple, you get 2 to the third times 3 squared times 5. When you multiply these two numbers together, you'll also get 2 to the third times 3 squared times 5. I hope this Venn diagram explains more of the concept behind it. And I'm pretty sure there is some sort of proof out there for this, but I will be relying more on examples so that you can understand in the context of examples and not necessarily with words, right? Because when you have mathematical definitions and explanations, sometimes they use tricky terminology. You don't quite understand how it was applicable. That's why I think examples are very useful for showing how this works. And so are diagrams too, like this Venn diagram right here. And I would say, again, I'm pretty sure I mentioned this before, but I would love for you guys to have more diagrams in your homework sets. Because really, sometimes the problems are pretty difficult to understand, and it's very helpful if you draw a diagram explaining what's actually going on. Alright, enough of my rambling. So, problem 6, and that's how we're going to show why knowing that the greatest common factor times the least common multiple is equal to the products is useful. And that's for this one problem, problem 6. If the greatest common factor of two numbers is 8, and the product of the numbers is 2,880, what is the least common multiple of these numbers? So, greatest common factor, GCF is equal to 8. Product of the numbers is 2,880. Well, we know that the GCF times the LCM, least common multiple, is equal to product of nums. And I feel like I should mention this right here only applies when you're finding the greatest common multiple or the least common greatest common factor or the least common multiple of two numbers. So there's a rule for 3 numbers. I will not get into it in this video, but there's a rule for that. It doesn't work the exact same way as this. And you'll see if you recall our last discussion about Venn diagrams, and we talked about the inclusion-exclusion principle, right? So if you have 3 numbers that look like this, you'll see that you'll be overcounting some parts. For example, perhaps these parts, because these overlap, right? And you'll overcount this part, and you won't arrive at the right answer. There's a rule for it. It's not this. But for our purposes, for our 2-number question, 2 number that we're finding the greatest common factor and least common multiple of, this does work. So we have 8 times the least common multiple is equal to 2,880. Then we have to divide by 8 on both sides to get the least common multiple. And the least common multiple is Hold up a minute. Question mark. Did I do my math wrong? Okay, 2,880 divided by 8. I make an effort to say these things out loud, but my math apparently is not good when I'm speaking aloud as I do it. 360. So least common multiple is 360. And this is a warning to myself not to talk too much during our cows competitions. Alright, least common multiple is 360, which solves our problem for problem 6. Least common multiple of the numbers is 360. And if you were inclined to do so, I guess you could draw out a diagram of what that would look like, of what the two numbers is. And I'm pretty sure there are a lot of numbers that this could be. So if you have your Venn diagram and you have your two mysterious numbers, we know that the least common we know the greatest common factor is 8. We know we have two numbers here, like A and B, and A times B has to equal 360. And so this, not A times B, 8 times A times B is equal to 360. So A times B is equal to 360 divided by 8. So A times B has to equal 45, and I'm pretty sure this could be applicable in another question. For example, what is the greatest sum of two numbers who has, a greatest common factor of 8 and a least common multiple of 360? Anyways, I am kind of getting off topic. Thank you guys for watching this video. We're going to be talking more about number theory, and this is more focused on number theory that you probably haven't learned in school. We're going to be talking about factors, yes, but we're going to be going more deeply, and this relates to counting too. We could briefly cover factors in our counting unit. Anyway, stay tuned for that. I'm going to be ending this video now.